So good afternoon, everyone. I'm Raul Flores, and these are Samuel Stewart and Travis Douglas. And today we are going to be talking about the experiment that we did at the GWATS Beamline in the APS last week. This experiment was intended to get some understanding on how we can use X-ray to improve the structure and performance of photovoltaic thin films. So here is the outline of the presentation. First, I will give a little bit of introduction to the technique. Then I will describe the capabilities of the Beamline that is in the IPS facility. Then we'll talk about the experiments and we will present the results. And finally, we'll give some concluding remarks. All right. So we just have a talk about SANS and SACs. Those are transmission mode techniques. Now I'm going to move and talk about the Grazing, Incidence, X-ray scattering. So Grazing, Incidence, X-ray scattering comprises several techniques that can be used to study nanostructures in both solids and liquids in a non-destructive way. So the way that these nanostructures scatter X-ray is very similar to traditional X-ray diffraction. However, there are two main differences. The first one is that usually we need to use a synchrotron source, and this is because of the size of the sample that we are trying to probe. And the other one is that the geometry itself. So we usually don't use the pi to pi, but we use a Grazing incidence geometry. This means that the grazing angle is very close to the critical angle for a total reflection. So depending on the magnitude of this angle, the Grazing incidence X-ray scattering techniques can be divided into two types. One is called Grazing incidence small angle X-ray scattering, and this allows to prove structures higher than 1 nanometer, and the other one is called Grazing incidence wide angle X-ray spectroscopy, which has a better capability to prove structures less than 1 nanometer. So from the scatter pattern of these techniques, we can determine the shape, the size, the internal structure. Not only that, but we can also see if the sample is crystalline and amorphous, or if there is any porosity. Among the benefits of this technique, we have that they can prove different length scale, but just a small variation of the angle. And we can also complement the result of electron microscopy. And also, this technique requires low sample preparation. So this slide shows a graph that lists the number of publications that have used this technique. So the first time that the technique was used was in 1989, and we can see almost an exponential growth in the use of the technique. And this is because it's a really powerful tool to prove different kinds of materials, including surfactants and emulsions, nanostructured surfaces, biological samples, polymer fibers, and so on. Fibers. So the beamline that we use for this experiment is located in the sector AIDE. It works with a fixed energy of 11 kiloelectron volts, and it supports both small angle and wide angle. In addition to that, it also has different sample environments, including solvent annealing cells, variable temperature cells, vacuum cells. It also has an in situ spin corer that allows to do in situ experiments, and it also has a filmetric UV that so you can measure the thickness of the sample in situ when you are doing spin coring. So here is the beam layout. So pretty much we use the beam that is produced at the source. Unlike other beams in the APS facility, we don't use a lot of optics to collimate the sample, so which means that we have good both space and temporal coherence, and we only use these slits to define the size of the sample, which is going to be incident on the material that we want to study. So the sample is usually placed in a diffractometer stage, which allows to move the sample in different angles, and it also has a 2D detector that can be moved away from the sample, whether when we want to do GSATS experiments or GSAX experiments. So the distance that also defines the resolution of the Q value that we want to for the sample.
So what we wanted to study with grazing incidence wax was a organic thin film solar cell. And I'll explain how this works in a bit, but basically you need two chemicals, this P3HT and this PCBM mixed together to make this solar cell work. And one of the advantages of these types of solar cells is, again, they're made thin films, they're very flexible these days, so they're a perfect sample for the technique to study with grazing incidence, because you got to have that grazing incidence to look at the thin film. So here's an example of a, we'll call it traditional bilayer solar cell, where we have our P-type material or donor on one side and our N-type on the other side. In this case, P3HT, the polymer, is the donor, and PCBM, the carbon ball, is the acceptor. Now, sunlight enters and excites the donor material, P3HT. This creates an exciton, which is an electron hole pair. This exciton can diffuse around in the material, and if it makes its way to a boundary of the donor-acceptor interface, it can dissociate into its separate charges, and those can be drawn to their respective electrodes, and that creates your electricity from sunlight. So that's the idea. Unfortunately, the exciton diffusion length is only about 10 nanometers before it recombines. So these days, people mix these two materials together in a single solvent and then spin coat the material, and you get this bulk heterojunction morphology shown here, where we have carbon-rich regions and P3HT-rich regions in the blue. And the idea is to reduce the amount of spacing between the two regions on average, and so the exciton is more likely to make it to a boundary and diffuse. So one thing about P3HT is that it's a polymer, but it forms into these blocks and kind of at a semi-crystalline behavior. So you can see here's one example of P3HT on the left, but it organizes into these blocks or these tilings. So there's clearly the carbon backbone is aligned up and down. We call this lamellar spacing. But also you can see these carbon rings are stacked on top of each other in this direction. So those are two different length scales. We have a shorter carbon ring here, stacking called pi to pi. And we also have a longer distance here between the two backbones called lamellar. So if we look at an example G-wax pattern, this is how P3HT forms in a cartoon form on a substrate. So Z is out of the plane, and here we have a plot of QZ, the momentum transfer, and we have a QX plot as well. What you see is there's two features. There's one on QX at this far Q. Well, that means we have something that's low in D spacing. So we can identify this as the small spacing between the carbon rings here. And we have these lower Q spacings here. So those are farther apart in real space. So that must be the distance between the carbon backbones. We can relate this to performance and efficiency of the solar cell. One thing to notice here real quick is that these aren't perfect peaks or spots, but they kind of have this arc behavior. That's because there's slightly disoriented alignments of these P3HT. They're not perfect. If they're perfect, they'd have a dot. If they're completely amorphous and isotropic, they'd have a ring. So to study this, we had one sample spun coat as it is, and we looked at the morphology. Another sample, we annealed it after spin coating and see if that heat treatment can improve the performance by adjusting spacing information. And to use a calibrant, we had to have one P3HT film by itself, just so we knew what that looked like as a standard.
Okay, so here's some of our raw data. So to remind you of the geometry, like they've said many times, we have a grazing incidence, incident beam coming onto our flat sample of a silicon substrate with some photovoltaic mixture on top. The incident beam, due to be under the critical angle, the illuminated volume is the footprint of the beam and then some small depth that's penetrating into the sample. So we're just looking at the contribution from the area of interest from the surface. It's coming back up, and here we have a beam stop that's stopping the direct beam and any specular reflection that might be present. And with this blocking, we can see these smaller intensity features in Q space. And so in a general sense, up on the detector is an increase in QZ, and then QX and QI are changing in a slightly complicated way as you go laterally in this image. So the idea is, as Sam said, to produce some line cuts, and so look at the intensity as a function of a line such as this or such as that. Seeing features where they are in Q space and how big they are in Q space in the QZ can tell you about the ordering in that direction. Seeing lateral features will tell you about lateral ordering. So why couldn't I just process this data very quickly and just give you some line cuts? Well, there are two issues. One is you can probably see is these black bars. So the detector is made out of what I assume to be very many smaller detectors, 8 or so in total. And the easy way to patch that is just to take this 10 seconds exposure of data, move it slightly, take another 10 seconds, and you can patch them together in an intelligent way. The other is, like I said earlier, when you look at the scattering geometry, the mapping of these pixels to Q space is not going to be just a linear, this is QI, this is another QI, it's just a linear mapping. It's very trigonometric. So that's not impossible to do, but it's more easily done by software. So at 8ID, they have some software they've made in MATLAB that can process this data very quickly. I haven't saved the results from that computer, so we'll just look at a qualitative viewing of our data. So here, this is just 100% P3HT, and we can see what Sam was seeing earlier was that lamellar ordering of these patches here. They're not dots, they extend in a kind of arc-like fashion. And so, like he said, instead of being perfectly oriented, there's a kind of distribution of orientations of those. So right away. Our other two data sets that we'll show is this blend of the P3HT and the PCBM. So the acceptor and the donor for the electrons. The PCBM, you saw it was a fullerene, I would say molecule, with some addition on it. It's not a very ordered substance, so it kind of diffracts in these rings. And is kind of drowning out the P3HT signal. You can look at where in Q it is to get an idea of the spacing involved, and then the width of these features will tell you about the size of the real space features making this pattern. When we anneal the sample, so at 150 degrees C for 30 minutes, a lot of the features change. We see this recurrence of the P3HT in a smaller dot than before instead of an arc, and so we can imagine that the ordering is getting better with the P3HT. But if we look at the line cuts where that correspond to domain sizes of these acceptors and donors, we can see them usually getting smaller and thinner. And so smaller in Q space means larger in real space. And so what that means, the domain sizes are increasing rather than decreasing. We would like the domains to decrease in size so that the excitons can diffuse over to a domain wall before recombining. That would let the solar cell work more efficiently, but that doesn't seem to be happening after this annealing treatment. So our conclusions is this treatment does order the P3HT better, but as far as the solar cell capabilities, it's probably going to decrease the effectiveness of them. So we wouldn't want to do it for this particular sample. We don't have an acknowledgement slide, but of course, we'd like to thank the 8ID scientists at APS, the NXS organizers, and fellow students for making it very fun. So. Any questions? Yeah.
What is the thickness of the thin films that you can be using?
So the skin depth, I don't have the numbers in my head. There's an easy formula pretty much to estimate what you're going to see, but it's on the order of nanometers, I believe. So it depends on the absorption coefficient of your material. Yeah.
Same
Yeah.
idea. What's the critical angle for these materials?
So the silicon if I remember correctly, is 0.16 degrees, roughly. This one was taken at 0.14 degrees. So the silicon, again, depending on the densities of the material up top, I think should be have the highest critical, or no, sorry. We're below the critical angle for silicon, so we're not going to penetrate in there. You know, you'd maybe have a problem if you're, yeah. So the materials themselves depends on their densities. I'm not sure. Do you remember? Okay.
No, it's 0.14. Yeah.
Oh, okay. Yeah.
How essential is that the sample be very flat?
Flat in the sense of roughness.
Flat, or is that important or not? What if it's rough?
So the roughness would destroy any kind of specular signal that you would want. And we're looking at the, I'm not sure if I want to call it diffuse scattering exactly, but it's definitely, it's not satisfying the specular condition. I'd imagine with extreme roughness, your signal might be difficult or lower, but I'm not sure on the bounds of the allowable roughness. These were spin coated, so it's tough for me to say if they were microscopically smooth or atomically smooth at that point. I don't think they would be too smooth.